Okay, perfect matching in graphs. First, the definition of a perfect matching is when we have a graph, we want a set of edges such that every vertex of the graph is incident to exactly one of the edges in the set. An example of this would be all the stable marriage problems we had. If we consider this to be a graph of men and women, then every matching between them was a perfect matching. Okay, so let's look at whether trees can have more than one perfect matching or not. Okay, so the way to approach this problem would be first to draw some pictures of trees and see if you could construct a tree with more than one perfect matching. And if not, then we'll try to prove the statement true with contradiction. So the proof by contradiction works by assuming that there's going to be at least two perfect matchings. And since we want the perfect matching to be unique, we want to show that these perfect matchings are actually the same. So, in other words, if two perfect matchings are the same, then they share all of their edges. So let's take these two perfect matchings that we have and remove all edges which are common to both of them. And when we do that, we end up with some vertices and edges such that every remaining vertex is incident to exactly one edge of each perfect matching. So the only way that this is possible is, in fact, if we have a cycle. So maybe this would be one perfect matching, and the other one would be this one. And therefore, we must have a cycle. And this contradicts the fact that trees are acyclic. So that would be one way of approaching the problem. Another one would be to do induction, but there were a lot of problems with the inductive approach. For one thing, many students, when they remove an edge from the tree might actually end up being disconnected. And if the tree is disconnected, then we can no longer apply our inductive hypothesis because trees must be connected. So one way of doing the proof by induction was to strengthen the inductive hypothesis in order to encompass forests. So a forest is basically a collection of trees. Another problem is that typically tree induction is when you have some sort of tree, you'll want to remove the leaf node, because when you remove a leaf node, you can guarantee that the rest of the tree will be connected and therefore remain a perfect matching. The problem with this approach, however, is that if we remove this leaf vertex and then apply our inductive hypothesis to the rest of the tree to find a perfect matching in the rest of the tree, what we'll find is that because this node right here is a leaf, we see that this edge which connects the leaf to the rest of the tree must be a part of the perfect matching. And that means that a perfect matching on the rest of the tree must have this vertex, the parent of the leaf, connected to the rest of the tree by exactly one edge in the perfect matching. But that means that this parent node would actually be incident to two edges in the perfect matching if we add back this edge into the perfect matching. So all of this is saying that removing one leaf does not work here. We actually have to remove both the leaf and its parent. The problem also with doing that is if you remove the leaf node and its parent, then the tree could end up being disconnected. So the argument is a bit subtle. What you have to do is eventually you have to show that there's some parent that looks like this. So the key is that the parent must have degree less than or equal to 2. Actually, the degree must be exactly equal to 2. So in this case, if we remove both the leaf and the parent, then we know that there must be at most one perfect matching in the rest of the tree. And then we know that this edge must be in the perfect matching of the entire tree because it's the only edge which is connected to this leaf. Therefore, the unique perfect matching in this tree must be the perfect matching of the rest of the tree plus this edge. So in order to justify that such a parent node exists, we first notice that suppose we had a parent with multiple leaves. In this case, there can be no perfect matching because each of these edges must be in the perfect matching, and that would contradict the fact that the parent must be incident to only one edge in the perfect matching. Therefore, if we have a parent with degree greater than 2, the case we must have is one leaf, and the other children of this parent must not be leaves themselves. So in this case, what you can do is keep following the children of the parent, and you're guaranteed to reach this point where you have one parent of degree 2 and a leaf. So at that point, you can remove the leaf and the parent and apply the inductive hypothesis, and you'll end up with at most one perfect matching in the tree. Okay, problem 2. If a graph has a perfect matching, it is two colorable. In other words, each vertex can be assigned one of two colors so that no two adjacent vertices have the same color. So this is kind of playing off the idea that maybe if you drew some diagrams of trees in the previous part, you would end up seeing that a perfect matching, in a sense, must alternate edges if you have this sort of line-shaped structure. So if you have this kind of alternating edge pattern, then maybe you could two-color it by assigning every other edge a different color. Fortunately, this does not work. The reason why is, in order for a graph to be two-colorable, we actually must have the degree of every vertex must be less than or equal to 2. So to think of a counterexample, we could think of the complete graph on 4 vertices. So in this case, we have a perfect matching. The perfect matching can be, for example, this edge and this edge. And we can see every vertex is incident to exactly one of these edges. And this graph is not two colorable because we could see the degree of every vertex is going to be 3. So if you want this vertex to have a different color from each of its neighbors, then you're going to need at the very least three colors. Finally, we have this question. If G is a simple graph with 2n vertices such that every vertex has degree greater than or equal to n, then we must show that it has a perfect matching. And the hint suggests using the fact that this graph must have a Hamiltonian cycle in order to show that there's a perfect matching. So first, let's reason to ourselves why the existence of a Hamiltonian cycle implies that G must have a perfect matching. So a Hamiltonian cycle is a series of edges which visits each vertex exactly once. So we could visualize it like this, and since there are 2n vertices, this Hamiltonian cycle is also going to have 2n edges. And the perfect matching is just given by taking every other edge in the Hamiltonian cycle. So that gives us our Hamiltonian cycle implies perfect matching. The tricky part about this question is proving that this graph must have a Hamiltonian cycle in the first place. So there's various ways of approaching this with induction. The way we approach it is by considering the largest possible counterexample. So what do we mean by the largest counterexample? We mean a graph G prime that satisfies P and has as many edges, or the most number of edges out of any counterexample. But since we're talking about a counterexample, we must have that it does not have a Hamiltonian cycle. Okay, so first what we're going to do is show that G prime has a Hamiltonian path. Okay, why is this true? This is true because we're considering the largest possible counterexample. So suppose that G prime does not have a Hamiltonian path. Then it has some path which is its longest path, but its longest path is not a Hamiltonian path. So what we can do is we can extend the longest path. So we could build a graph G prime, G double prime from G prime, which takes its longest path and extends it by another edge. Also, this new graph, G double prime, must not have a Hamiltonian cycle. The reason why it does not have a Hamiltonian cycle is because when we extended this path, we know we can't get a cycle out because this path originally did not visit every single vertex. So if it does not visit every single vertex, we could just add another edge to a vertex that has not been visited yet, and we would end up with a longer path but not a cycle. So this graph does not have a Hamiltonian cycle either, but compared to G prime, it has one extra edge. So this contradicts the fact that G prime was supposed to be the largest counterexample. So here we've shown that G prime has a Hamiltonian path. Now we're going to also show that G prime has a Hamiltonian cycle. So how do we do this? Essentially, we take the Hamiltonian path and we're going to extend it and make it a Hamiltonian cycle. So the Hamiltonian path looks something like this. We start off with vertex 1, vertex 2, vertex 3, all the way until the last vertex, v sub 2n. Okay, so if we know that there's an edge between v1 and v2n, we're already done. There's already a Hamiltonian cycle. So now we just have to consider the case where there's no edge between these two. So in order to do this, we need the degree condition that every vertex has degree at least n. And let's look at v1 and v sub 2n. So v1 has one neighbor, which is v2, so therefore it has n minus 1 other neighbors. And same with v sub 2n. What else do we know? We know that all of these neighbors must lie within v2 up until v sub 2n minus 1. And the reason for this is that, well, v1 can't have an edge to itself, and we're already considering the case where v1 does not have an edge to v sub 2n. So we have n minus 1 neighbors of v1 in here, and n minus 1 neighbors of v sub 2n in here. So these total up to 2n minus 2 neighbors. And over here, we have 2n minus 1 minus 2 plus 1 equals 2n minus 2 vertices between v1 and v sub 2n. So since these numbers match, what we can conclude is that there must be some adjacent pair of vertices such that v1 is connected to some vi plus 1 and v sub 2n is connected to v sub I. And we already know there's a Hamiltonian path from v sub I plus 1 all the way to v sub 2n. And we already know that there's a path from v sub 1 to v sub I. So if we look at all of these edges together, then we see that there's a Hamiltonian cycle.